In the previous video, we had discussed the basics of reinforcement learning algorithms. We had also motivated how deep learning can be used in order to improve reinforcement learning algorithms in cases where the state space is very large. However, all the methods that we had discussed in the previous video had only used Monte Carlo simulations in which the ground truth could be obtained only after the full simulation is performed. In many cases, we may have very long Markov decision processes or continuous Markov decision processes. In such cases, the learning must be performed simultaneously along with the actions. In such cases, an idea known as bootstrapping is very useful. The idea of bootstrapping substitutes the knowledge of the absolute ground truth with an improved ground truth obtained by improved predictions of the same algorithm by using a partial level of look ahead. The previous video discussed how value functions can be learned for shorter episodes. In that approach, we updated the state action value table for each episode with Monte Carlo simulations. This was essentially a direct generalization of the multi-armed banded epsilon greedy algorithm where values were being maintained for all possible states encountered. Now, this type of approach, it's effective for games like tic-tac-toe, which have small episodes, because a tic-tac-toe only has 9 positions on the board, so a game lasts for only as long as 9 moves, so each episode has a relatively small length. However, not all reinforcement learning settings are quite as simple. So in many reinforcement learning settings, such as robots, the actions may occur continuously over long periods of time. So the robot is continuously learning as well as performing actions. So clearly you don't have even an episodic Markov decision process, and under such circumstances the learning needs to occur. So Monte Carlo simulations become much harder. So let's look at the concept of an infinite Markov decision process. So this is just like the finite Markov decision process which we introduced in the previous lecture, except that here the sequence below has infinite length because it's a continuous process which occurs over time. So you can see I have annotated states by SI, actions by AI, and rewards by RI. So you always have this cycle S0, A0, R0, S1, A1, R1, and this sequence keeps going on all the way to infinity. So the cumulative reward RT at time t is given by the discounted sum of the immediate rewards for some discount factor gamma. So you have capital RT, which is the expected reward at time t. That is given by the current reward plus the discounted reward. You apply as this is a simple discounting, geometric discounting with time. And the idea behind the discounting is that the future rewards are worth less than immediate rewards, and choosing gamma less than 1 it is not essential for episodic processes. However, if you recall, even in the last lecture we had always used some discount factor. So the earlier moves in tic-tac-toe, they were given less credit for a win compared to the later wins which more immediately contribute to the victory. But that's not essential for episodic processes. You can work with gamma is equal to 1. However, if you have an infinite process, what happens is that if you look at the summation of equation 1, it could go to infinity. So, but when you choose gamma less than 1, you're not going to have an unbounded summation. It's also going to make your training process stable. It's not going to cause instability. So choosing gamma less than 1 is essential for continuous MDPs. Now, since we are going to generalize this Monte Carlo updates which we discussed in the previous lecture, let us revisit the algorithm that we discussed in the previous lecture for the greedy algorithm, the way we generalize the multi-armed banded greedy algorithm for tic-tac-toe. So the way this was done is that for each state, that means for each position in the board of tic-tac-toe, we maintained the average values of the state action pair. So what's that average value? That is an average discounted reward at the end of the game. And this table was initialized to small random values. Then we would simulate a game of self-play using epsilon greedy. So at each position, we would, from the perspective of the player, pick the best possible move based on this table, simulate that game right up to the end, and then at the end you'll get a reward +1 or -1, and then for all the positions in the board that were played in that game, we update those averages to include the effect of this newly played game. And this type of approach, if you repeat it over many steps, over time, the algorithm is going to learn the optimal strategy of playing. So it's also going to learn what the traps are in tic-tac-toe, what are the best strategic moves, because statistically what's going to happen is that when you simulate these self games and you play over time, then over time it's going to learn that certain types of moves over time they tend to win. So that is how the optimal strategy is learned by this type of approach. Of course, this is for the episodic process where your episodes are short. So let's look at how we can modify this approach when we have a long Markov decision process where our length, we can't just wait till the end of the process to update. Now, the basic idea behind this approach of updating online, updating after each move, comes from the notion of bootstrapping. So, what does bootstrapping mean? Bootstrapping means that you don't really use a true ground truth for learning. Now, note that in our Monte Carlo simulation, we wait till the game ends, then we have a true ground truth, has who won the game. Here, what we do is that, well, we don't play it all the way up to the end. We play it a little bit ahead. We do a partial simulation for a few moves. That can improve our prediction because you have a way of evaluating every state on the board. You have this table of state action pairs. But if you move a little bit ahead, you have seen more of the game and your prediction will be a little bit more accurate. So that's the basic idea. You use the improved prediction as the ground truth for the current timestamp. So think of a situation where, for example, in tic-tac-toe, you have a parameterized evaluation function for the board. So given an input board, you have some way of producing a parameterized evaluation. And the evaluation is not perfect, but it gives you some reasonable estimation. What you can do is that you play your move, and after the opponent plays the next move, that, by the way, the opponent playing the next move can also be from the same evaluation function, except that you're playing from the perspective of the opponent. You look at how the evaluation of the board has changed. Does the evaluation look more like we are going to win, or does it look more like the opponent is going to win? And that tells you something. That tells you that there's something in your evaluation that was not included in the current timestamp, which the future will tell you. So you can use that as a ground truth. So that is what is called temporal difference learning. So you use the difference in prediction caused by partial look aheads. So in Monte Carlo simulation, you use full look ahead right up to the very end and use that as a ground truth. Here you use the prediction of your algorithm itself, of the same learner, except that you're cheating a little bit. You're looking a little bit ahead, you're looking for a few moves, you're improving the prediction, and then you're using that as a ground truth for learning. That's what is called bootstrapping. So to understand bootstrapping a little bit further, I'm going to give you an example of chess. And board games are a perfect example of this, because in fact the first use of this type of approach was used very early on in Samuel's checkers program. Arthur Samuels from IBM, he had created a checkers program where he used the basic idea of bootstrapping. Now let's look at this from the perspective of the chess, because many of you might be familiar with these software programs where you evaluate the program where the program evaluates a minimax tree of game moves for various plies, and then it makes the best move. Now, you might have noticed that in the program, you can set the strength of the program depending on the ply. So, for example, if you play at 1 ply, it will play in a naive way, but if you play it at 10 ply, it will certainly play very strong. So one question arises is that why is the minimax evaluation of a chess program, which is a tree of possible moves, at 10 ply stronger than that using the 1 ply board evaluation? The reason is that the way these programs work is that they have an evaluation function at each board position. Now this evaluation function is obviously not perfect. So for example, if you evaluate at the current position, it's not going to tell you really much about what the board is going to look like 20 moves down the road. It's going to evaluate something based on the amount of material you have, the safety of the king, all these types of factors. It's a heuristic evaluation function. But 10 moves down the road, you have a lot more foresight about what has happened. You know a lot more things have happened, and suddenly, if you are using all possible moves, the best move from the perspective of the opponent and the best move from your perspective, and you take that minimax evaluation and leaves at 10 fly further down, suddenly that same evaluation function, this weak evaluation function becomes very strong. Now note that if your evaluation function had been perfect, so let's say you had God's evaluation function at a given position of the board, that means that you could tell just by looking at the board which position is going to win, lose or draw. In fact, in checkers, you have a way of doing that type of evaluation. Today, you have a way of doing that type of evaluation. Now, in that case, it doesn't matter how many ply you look down. No matter whether you look at 1 ply or 10 ply, you will have perfect evaluation. It's only when working with heuristically imperfect evaluation, looking ahead tells you something about the errors that your imperfect evaluation made. And the fact that these are errors gives you the basis to correct these errors. It tells you that what the evaluation is 10 ply down should be used as some kind of ground truth to correct the errors that you made at the current point. Now, this basic idea was what was used by Samuel's checkers program, and this program was referred to as TD leaf. And a variant of this idea was used in many subsequent successful systems. One was TD gammon. Now, AlphaZero, it isn't exactly like this. It uses a different kind of policy bootstrapping. But the basic principle is somewhat similar. Now, let's introduce the notion of QLearning. So, QLearning is based on the same notion of look ahead that we just discussed, but except that instead of minimax over a tree, we can just do one step look ahead. So let's look at a simple case where we just look one step forward and we do the bootstrapping. So let's say that you maintain this table of state, the values of state action pairs, that's QST80. Now this is the same table of the best values of actions for each state that you use for your Monte Carlo simulation. So remember we had this greedy algorithm for tic-tac-toe. And here again you had maintained, in this greedy algorithm again you had maintained the best action for each state. You maintain those average values using Monte Carlo simulation. But let's say that now you have this table of state action pairs. And what you do is that for the value of QST80, you play tic-tac-toe with epsilon greedy. Now, let's say that you initialize QST80 to random values. And each move again, you play with epsilon. You're doing Monte Carlo simulation just like we did it in the previous case. But the difference is that after each move, you make an update. You don't wait till the end of the game. So, after this move, what you say is that if I do a one-step look ahead and I get to state ST plus 1 and I look at the best possible move in the next position. So you can see there's a max over all possible actions of QST plus 1. So the next board position A, and the gamma is the discount factor. So you have RT plus gamma times max QST plus 1A. Now, the way this comes is because you have this reward function which does the discounting, right? You have RT plus gamma RT square. So that's why that's where you get the discount factor from. So if you do this type of update, you are essentially what you're saying is that I'm looking one step ahead into the future. I'm looking at the change in the board evaluation. I know this change occurred because of the imperfectness of my information at the current step. And after looking ahead at one step, I know a little bit more, so that evaluation is maybe a little bit better. So I'm going to update the value of my state add for state action pair by using this one step look ahead to the value of RT plus gamma max over all actions QST plus 1A. So, of course, this is a little bit aggressive because, especially in stochastic processes, if you do this type of update, it can cause instability. So, one thing that people do is they introduce a learning rate. They don't do the full update of equation 2. They do exponential averaging. So, whatever my current value is, so you have alpha, which is your parameter for exponential averaging. You weight the current value with 1 minus alpha and this updated value with alpha. So, this just results in more stable learning. Now, the question arises, why does this work? So let's look at the tic-tac-toe as an example. So let's say that, after all, we are starting off tables containing completely random values. Why should updating in this way give you improved values? So the idea here is that when you do these updates, yes, it's true that the values on the right hand side of equation 2, the QST plus 1A, initially are also wrong values, they're random values. So most of these updates don't really help you much. However, when you're looking at this update is different when your state is terminal. So this equation 2, when the state is terminal, when it's the very last state, this is it will be a meaningful update. So imagine at the very last state when you have two crosses the line and you put one more cross and you win the game, this value of this QST plus 1A will be 1 or minus 1 depending on who wins. So you are going to get an absolutely correct evaluation for the very last move of the game. So what's going to happen? So the update of a value, so this equation 2 that you use here, when your ST is a next to terminal state, the ST plus 1 will be a terminal state. So it's going to give you a perfect evaluation. So what's going to happen? Your next to terminal state will suddenly become informative. And the next time, what's going to happen is that when the next to terminal state occurs on the right hand side of this Bellman, of this equation 2 over here, your next to penultimate state will become better. So over time, these values, these informative values will propagate. And we will converge to the proper values of all state action pairs. Now, Sarsa is a variation of this theme. Now, note that Sarsa stands for state action reward state action. Now, in the case of Bellman's equations, we are looking at the best possible move in the next timestamp. However, when we are performing the actual update, the way the self play is being performed, you are using epsilon greedy. The way the Sasha is performed is that you perform the update using the same approach that you use for performing the next step. So what you do is that you perform the simulation for the next step with the epsilon greedy policy. You observe ST plus 1, you observe AT plus 1. And you, for the observed value of ST plus 1, AT plus 1, whatever you actually observe using epsilon greedy, you create the bootstrapped estimate, that is RT plus gamma ST plus 1, AT plus 1. Now note that this Sarsa update would be the same as the Bellman update if you set epsilon is equal to 0. So what you're doing is that your bootstrapped value will also include the effect of the exploration. In Bellman, your bootstrap value, you're always looking at the best possible value in the next timestamp. But when you actually perform the move, you'll perform some exploration. You will with probability epsilon you'll pick a random move. Here, what you're doing is that in the case of Sasha, your whatever random move you pick, even if you pick a random move, your improved estimate of QST will include the effect of that, and then you perform the same update. If you look at equation 3, it's pretty much identical to the equation 2 over here. The difference is that in equation 2 you are using the best possible approach, irrespective of what exploration you perform, irrespective of whether epsilon greedy picked a random action. And in equation 3, you are including the effect of picking that random action. You're not picking the max. You're first looking at the best possible move up front, then you're picking that with probability 1 minus epsilon. And with probability epsilon, you might pick some random action. And of course, just like in the case of Bellman, you can have a more stable variation of this algorithm where you have a learning rate alpha, and you can weight the current value of QSTAT by 1 minus alpha and the updated value by alpha. So let's look at the difference between the Sarsa update and the Bellman update. This is the difference between on-policy evaluation and off-policy evaluation. Now note that in both algorithms we used epsilon greedy. So for example, if we had tic-tac-toe, we would use epsilon greedy to simulate tic-tac-toe all the way to termination. However, in the case of Bellman, we did not use the actual move that was made, the look ahead to the actual move that was made in order to get the bootstrapped value. We did a look ahead to the best possible move in order to set up a bootstrapped value. In the case of Sarsa, we actually we included the effect of the exploratory action, so our bootstrapped value might not necessarily be optimal. So the question is, why should we ever pick a suboptimal value for bootstrapping at all? Why not always use Bellman? After all, Bellman it is the optimal possible value of state, and it seems logical that we should use the maximum possible value. So the reason for this is that techniques that need to be used continuously. So for example, if you have a robot which continuously needs to learn as well as to predict at the same time, in that type of application, on policy learning is more useful. On the other hand, if you had an application, for example, like tic-tac-toe, where you do all the learning up front and then you fix the model. So whatever table you learn, you just fix it, and then you can perform the simulation with a full greedy policy. That means you set epsilon equals 0, no more exploratory actions, all the exploration and learning is done, and you just play the games according to whatever the fixed policy tells you. In that case, Bellman is useful. Now, in the case where you always need to perform exploration during learning, it is very important to include the downsides of the exploration within the policy itself. So that's why on-policy learning is important. Let me give you an example. So let's say that you wanted to teach a robot to get from point A to point B by reinforcement learning, and you couldn't possibly separate the inference time from the training time. Now, there are two paths for the robot. The robot could take a very safe path from point A to point B, and it could take a little bit longer. Or the robot could take a path which is the shorter path, the faster path, but that path goes along the edge of a cliff. So now, if you had an ability to do off policy, so if you had the ability to do inference separately from training, it is okay to use Bellman, because then it can learn that walking along the edge of the cliff is okay. It's the shortest path, and as long as Bellman teaches it always to make the optimal move, it's going to make the optimal move and it's going to get there, because you're not doing exploration at inference time. However, in the case where you cannot cleanly separate the inference from the training time, where they are always occurring together, it is actually dangerous to use off-policy learning, because in that case what's going to happen is that even though it's the shortest path to go along the edge of the cliff, because from time to time epsilon greedy tells your robot to take a random action, from time to time it's just going to jump off the edge of the cliff. So that's not, so what's going to happen when you do on policy exploration, or when you use SARSA, your robot is going to learn that it's better off not being too close to the edge of the cliff. It's still going to try to stay a little bit close so it gets a shorter path, but it's not going to stay so close that it falls off the edge of the cliff, because it knows that by staying at the edge of the cliff from time to time, I'm going to do exploration, I'm going to fall off. On the other hand, in the case of the bellman, it's not going to learn that, because it's always looking at the optimal action for its next move. It's not going to include the effect of the exploration. So bellman would be useful only if you could train the robot up front, and then at the time of inference, when you want to actually use the robot for something useful, you actually use it in order by setting epsilon is equal to 0 in that case. And in general, of course, there are also some practical issues in these matters, because sometimes when you're dealing with physical robots, they tend to break. So even then, sometimes, even if you can cleanly separate inference from training, sometimes in those cases, it might be desirable to use on policy exploration, on policy learning. Now, let's look at how deep learning fits into all this. So far, we have not discussed the effect of deep learning. So here we had the case where we use tic-tac-toe as an example. So you could maintain the values of all state action pairs because the number of possible states in tic-tac-toe is relatively small. So let's go back to the case of the Atari game. Now, in the case of the Atari game, there are too many states of the Atari game for you to maintain the values of all possible state action pairs. So instead of maintaining a table, you have a convolutional neural network which takes the state as input, and it outputs QSTA for all possible moves. So let's say in your Atari game, your console gives you up, down, left, right. So it will give you QSTAT for each possible state action pair. So instead of QSTA, I'm going to use the notation FXT. Now XT is the feature representation of state ST, and W is the weight vector inside the convolutional neural network. So instead of learning the table of state action pairs, now we are trying to learn W. These are the parameters which enable the neural network to map the states to the Q values. So let's look at an example of the convolutional neural network used in the case of the Atari video game. This is actually from the DeepMind paper, and this basic architecture was used for Atari. Now note that the final output layer, they use the same architecture for all the Atari games, but the final output layer could vary, because if you have 4 actions, for example, up, down, left, right, the final output layer will have a softmax with 4 units, but it could be in some cases the game might have, for example, 18 actions, in which case the final output softmax would have 18 possible actions. So the details of this architecture in the DeepMind paper, and the input of course is your previous 4 screens of pixels. So you can see that the depth of the input layer is 4 because it corresponds to 4 screens of pixels, and this is 84 cross 84 because it's got 84 cross 84 pixels. So here again, you are using the same approach. We are using deep learning in order to perform the updates. And just as we used the prediction from one step ahead in the case of QLearning, we are using the same prediction from one step ahead. So you can see I have marked something as treated as constant ground truth. So you're setting up your loss of your neural network by looking by first, so for example in the Atari game, you perform an action, you look at the next state which gives you the state xt plus 1, you use the convolutional neural network to evaluate it, so that's fxt plus 1 wa, and rt plus gamma times that maximum of all possible values. So you're going to have to evaluate it for all possible actions, and that will give you the constant ground truth. That is going to give you the improved prediction using the look ahead, and you will treat that improved prediction using the look ahead as a constant ground truth, and you're going to look at the value in the previous timestamp when you didn't know this extra information with this one step look ahead. that as the value you're trying to correct using the loss functions. You're trying to correct the weight vector, so your current prediction without using that look ahead improves. So note that this value that I marked as constant ground truth, you have to treat it as a constant from the perspective of loss function. So when you differentiate, you are not going to differentiate this term in here, which includes the effect of fxt plus 1 wa, because you're treating this entire expression inside this RT plus gamma max of fxt plus 1 WA as a constant. So you can see that when I take the gradient of the loss function, you are only taking the gradient of the term corresponding to fxt WA. So you can see that in equation 6. You are never differentiating the term corresponding to fxt plus 1 WA. So this is your essential gradient descent updates. Now note that all these gradients that you can compute using the back propagation algorithm. So this is your deep learning version of the same QLearning approach which we discussed using the table of state action pairs. And you can do the same thing for Sasha. The main difference in the case of Sasha is that how you set up your constant ground truth is different. In the case of QLearning, you pick the best possible action. In the case of Sasha, you would you look at the action, the current timestamp, then you look at the state you get for the next timestamp, you again input it to the neural network, you find the best possible action, and then for that best possible action, you again perform the action using epsilon greedy, and you evaluate, and that's going to give you the loss function. So essentially this is on policy learning. So the way the on policy learning, again, just to recap, at the current timestamp you're going to input xt. It's going to give you all possible actions. So you pick one of these actions based on a fixed policy, for example epsilon greedy. Then whatever this xt plus 1 you get, it's going to change. It's going to, by performing this action, you're going to get a new state. That new state you again input in the neural network, and that is going to give you an output for again for all possible actions. And again, what you're going to do is that these all possible actions you're going to evaluate, and you're going to observe what those are. You're going to use that to get your output value. So that's how you're going to get your constant ground truth output value. So this is the only difference between the Sasha and your QLearning algorithm. Now there is a variation of the same. Now note that here the convolutional neural network in the case of QLearning and Sasha, it always outputs the value of all actions. You could have built a slightly different architecture of neural network where instead of output for each state action pair, you could just have output the value of the state. In fact, by outputting the value of a state, you can also implement the same algorithms, exactly the same algorithms, this QLearning and Sasha, except that it's going to require more evaluations of your network, because in the previous case, because you were outputting the value of all actions in one shot, you can explore a forward-looking policy of moves. Here, you're going to have to look at what the state is for performing each action and evaluate the action repeatedly in order to perform the same step. So let's look at this slight variant. So here, your value network produces GXTW. By the way, a close bracket is missing in the top bullet. I just noticed a typo. And you have a bootstrapped ground truth, that's RT plus gamma GXT plus 1W. And again, you're going to use this observed value to set up your loss function. And again, the gradient descents are exactly similar. So, and by setting up the appropriate policies, by using by pairing the same approach with appropriate policies and heuristics, you can actually implement both QLearning and Sasha exactly. And in fact, in the book, it's described how this can be done. Uh, the original forms of temporal difference learning, the way they were called TD0, they used this type of architecture where you were outputting a value instead of updating the outputs of all possible actions. But conceptually, there's no difference between the two. And this type of approach, it does have some advantages because in some cases, you may want to use some heuristic policy of look ahead. So you may want to look over a tree of moves. You may want to bootstrap over multiple timestamps. You may want to look at some heuristic policy using some combination of moves. In those cases, it is better to work with this type of representation. In fact, if you look at AlphaGo's implementation, they used this type of network. They used a value network instead of Q network. So sometimes with more complex policies where you are using some kind of combination of multiple look aheads, it's easier and simpler to work with this architecture. Let's look at bootstrapping over multiple timestamps. So for example, in temporal difference, it bootstraps over one timestamp. Now let's say you perform a strategically wrong move in chess. It may not show that the error may not show by looking ahead only over one timestamp. You may have to go through multiple moves in order to see that error. And if you look at on-policy approach, you can apply an on-policy approach where you simulate it for n timestamps and then you look at the evaluation, and using that evaluation you can perform the update. But this is a little bit weak because you're just looking at one possibility from the tree of moves. So the off policy, like Bellman, you can look at the entire minimax tree. So that's like looking at n-ply for a chess program, looking at the best possible evaluation, the optimal play by both players, and use that for bootstrap. In fact, this is what was used by Samuel's checkers program, and this was referred to as TD leaf by later papers. In fact, it was forgotten during the early years. And any optimization, in general, you can use any optimization heuristic for inference. And in fact, there's a technique called Monte Carlo tree search that is described in the book. So you could, in fact, explore multiple branches, look at the look ahead evaluations. You could average these look aheads, and you could set up a statistically robust target. You could do all kinds of heuristic approaches in order to do look aheads. Another principal way of doing look aheads is what is called TD lambda. So TD lambda is a generalization of TD0. So TD0 is the algorithm we described where you're using just one step. And here, what you do is that you use a fixed window n. Suppose you want to, no, not in TD lambda. First, let's look at the fixed window n update. So let's say you want to do an update based on n steps. So you can generalize this update in the equation I have shown over here, the equation 9, the short notation below. Now, if you look at the short notation below, this is the one-step equation. Here we are using a discount parameter lambda, where lambda lies between 0 and 1. So in this case, if you look at the update, for a fixed window n, so here this is gamma is the reward discount factor. So you are looking at n steps, you're looking at a temporal difference over n steps, and you're performing this generalized update. And in TD lambda, you include both lambda and gamma. Now gamma is the discount factor of the environment, and lambda is the discount factor of the algorithm. And the description of how they are different again is given in the book, and you perform this update using the TD lambda update. Now, if you set lambda is equal to 1 in the equation 10, you are going to get Monte Carlo simulations. And similarly, for the fixed window updates, the equation just above equation 10, if you set n is equal to infinity, again you are going to get Monte Carlo methods. More details of this multi-step updates are again described in the book. Now, what is the difference between Monte Carlo versus temporal differences? So, this lambda, in a sense, it regulates the trade-off between bias and variance. So, using small values of lambda is advisable if you have very small amount of data. But if you have lots of data, you can use larger values of lambda. You can get closer and closer to Monte Carlo simulation because it gives you a more unbiased result, but it has higher variance. So, you need more data in order to implement those. So, in order to understand this, how Monte Carlo method is different from temporal difference. If you look at a chess game, let's say that you're using a minimax evaluation for bootstrapping. Now, a temporal difference method, if you use a fixed number of plies, what's going to happen is that each time you make a mistake in the game, your policy has a mistake, it's going to show up as a temporal difference because the evaluation at n ply will be different from the evaluation at 1 ply. So, on the other hand, in Monte Carlo method, it's going to depend, the evaluation at all positions in the game is going to be different, and it only depends on the final result of the game. It's going to be a 1 or -1. And that's a key difference in terms of why it affects your updates in terms of trade-off between bias and variance. So let's look at a specific example. So let's look at a Monte Carlo rollout between two agents, Alice and Bob. So Alice and Bob are two AI agents. They can in fact be self-play agents, each playing using the same neural network, but from the perspective of each player. Now, let's say that in the Monte Carlo rollout, both Alice made two mistakes during her game and Bob also made two mistakes. But maybe maybe Bob's mistakes were a little bit more serious than Alice's mistakes. So Alice won in the end. And this is in fact quite common in chess games because both sides may have imperfect play, but one might win in the end depending on whose mistakes were more serious. Now, in the Monte Carlo simulation, it's not going to differentiate between good moves or mistakes of Alice and Bob. All of the moves in that game, are going to get a credit depending on the final evaluation of the game. It's not going to tell you anything about which move is better than the other or which move has what differential effect. So because Alice won in the end, then even Alice's mistakes, maybe they were minor mistakes, but even her mistakes are going to get a positive credit because she won in the end. And Bob's mistakes are going to be properly recognized, but there's going to be no understanding of the difference between Bob's mistakes and moves that were ordinary, because all of them are going to get the same credit. Now, unless you have more data, unless you have data from other games, it is impossible to use this data to develop any kind of learning. So if you have a small number of games, you're not going to be able to perform good learning with this type of data. On the other hand, in temporal differences, what's going to happen is that every time Bob makes a mistake, it's going to show up as a temporal difference because the board evaluation at n ply or even 1 ply is going to be different looking down the road with some look ahead as compared to the board evaluation at the current time. So it's going to give, every time Alice makes a mistake, it's going to give a warning, hey, a mistake was made. Or every time Bob makes a mistake, and that's the essence of temporal difference. Temporal difference kind of captures the error. It kind of tells you that if I could look a little bit more into the future, then what would that future tell me? It was an error made in the current time. So it tells you something more immediate, and that is why if you have less amount of data, you can learn more effectively with the method of temporal. It's more insightful. Now, this doesn't mean that Monte Carlo simulation is perfect, because if you had a lot of data, very often if you use, for example, TD0, it's not going to be able to understand strategically incorrect moves. So imagine in the opening, it made some strategically incorrect move. It doesn't show up as a temporal difference even over 10 ply. But because it was a strategic mistake, finally at the end of the game, the person loses. So in this kind of situation, temporal differences won't be able to catch it. So you can see that there's a clear trade-off between bias and variance. Now, this type of approach also has implications for other methods because policy. So in the next lecture, we will discuss policy gradients. And often in policy gradients, you have to decide what is the differential advantage of an action. And this is often very difficult in games without continuous rewards. And one approach that is used, of course, is Monte Carlo simulation to the end of the game. In fact, in policy gradient, Monte Carlo simulations are very common. to use, but often in order to reduce variance, a technique called actor critic methods are often used. So often what is done is that value networks are used, the temporal differences that you can obtain from value networks, they are used to decide the advantage of an action or the error of an action. And this particular notion of bootstrapping, in fact, it can even be combined with some policy-based methods. So sometimes you can even bootstrap policies. So in fact, if you look at Alpha Zero, the most recent paper from December, they actually show how to bootstrap policies and combine that bootstrap policy with Monte Carlo tree search. And a brief description of that is again given in the book.